Okay, so let's talk about topic 3. Before I get to this topic here, let's review a few of the things we've talked about the last few days. You guys ready? Okay, so this unit is all about combining our first 2 units together. Unit 1 was all about biology. We talked about things like ecosystems. Seabass, focus. Talked about ecosystems. We talked about populations. Guys, focus, please. Population, species. We talked about abiotic factors. Talked about biotic factors. Basically, we talked about life. How life exists, what it requires. Unit 2, we talked about chemistry, all about our chemicals. We learned about elements and compounds. Okay, this unit puts them together. What we're going to do is we're going to talk about how, to be honest, if I'm being blunt here, as humans, we kind of suck. We've polluted our world. Not necessarily to the point where it's uninhabitable, but environmentalism is really important nowadays. Whether or not we're talking about climate change or even just something as simple as like dumping our garbage on the ground. I grew up in the 90s, and in the 90s, there was a big push for the 3 R's. You guys ever heard that phrase before, the 3 R's? Reduce, reuse, recycle. This may seem strange to you guys, living in the world you live in, but back in the 90s, people littered all the time. It was such a common problem that like society had to like train people to basically not throw their garbage on the ground. Littering laws came into effect, where it's like you could get fined if you threw your stuff on the ground. And I got to be honest, in my lifetime, I've actually seen a difference in terms of most people now know put stuff in a garbage can. Like seriously, it's not hard, right? We now know to do things like recycle our cans, our bottles. Now it used to be that like a plastic water bottle, like the one in front of Kaylin there, we used to just throw those away. And now we know, no, let's recycle them. One thing that governments have then done is they've made it so that you have to pay an extra 5 or 10 or 25 cents every time you buy something as like a recycling fee, right? That's their incentive to encourage people to go recycle stuff. But believe it or not, 20 years ago, people didn't do that. The classic example is, I don't have the picture on this slide, but you know like the pop can rings, like the 6 little plastic rings? People used to just throw those away all the time. And then birds, fellas, stay with me. Birds and fish, they would get like their necks and their beaks and their gills stuck inside them. And so, to be honest, humans kind of had to learn not to basically destroy our world. And like we always discover new things there's problems for, like oil spills or air quality. We're going to talk about those about the next 2 days here. Today we're going to talk about water and how we want to try to not ruin our water supply. And then tomorrow we're going to talk about air, things like putting smog and carbon dioxide pollution into our air and ruining our world, basically. Okay? That's our unit. I've said this before. I think you know most of this stuff. Most people now know it's not a good thing to pollute, right? Like that's mostly obvious. Most of what we need to talk now about is like the vocabulary, the words we use, and maybe I'll show you a few new things along the way, but I bet most of the stuff you know. Okay. So today's topic is water quality. I've got a hypothetical question here. Here's 2 bodies of water. Which one would you rather swim in? And I think the nice blue aqua, pretty one that's got fish in it. Yeah. Because I don't know if you guys can tell, but that one that's on the left there, that's like oily, sludgy sort of stuff in the water. That is highly contaminated water. Okay. Maybe it doesn't look so bad to you, but that was not a pretty beach. That was like a picture of like some oil sludge washed up on shore. So unless you like bathing in oil. So I'm going to read right off the bottom slide here. I think one of the reasons why you guys know that the one on the right is better is clarity of water. What does clarity of water mean? How clear it is, yeah. This word right here, clarity of water, is basically how clean it is. How clean it is, how clear it is. In general, if it looks kind of dirty and gross and yucky, I have a 4-year-old, I use the word yucky. If it looks gross, yeah, you're probably not going to want to drink it or swim in it. This water right here, it looks good though. But maybe you still shouldn't drink the water, and maybe you still shouldn't swim in it. What it looks like is important, but today we want to talk about it's not the only indicator of water quality. There are many other things we have to consider before we drink or bathe or swim in or use water. Does that make sense? So don't just base it on how it looks. Chances are this is not nice water. However, I'm not guaranteeing you that this is great water either. It probably is, but it may not be. Does that make sense? So that's our goal today, talk about water quality. Here are 5 things you need to know about what we use water for. If I can give some advice, memorize them. To me, this is like a perfect test question. What are the 5 main things that we use water for? Number 1, we drink water. That's very important. We need water to survive. Water is one of the key compounds that we need. If you don't have access to clean water, it's a problem. We're very lucky in Canada. We're a first world country. We have water available for free pretty much anywhere. Like half you guys here even have a water bottle in front of you. You're hydrating. Good for you. It's awesome. If you lived in other countries in the world, though, a lot of African or Asian countries, you may not actually have water that's free. You may not even have water that is safe for drinking. It may need to be purified. So that is one thing that we use, though, for water. We need to drink it. Number 2, recreational uses. Yeah, that'd be a good example. Swimming, water skiing, like we put it in our hot tubs, right? Now, in those examples there, we're not necessarily talking about needing to drink it, but it still needs to be safe to go into, right? If the water is particularly acidic, I don't think you should go swimming in it. Okay, so that's recreational uses. Can you stop tapping whoever's doing that? Thanks. Next one here, livestock drinking water. I know that the 2 of these things are drinking here, but there are a lot of animals that need to drink water. And the reason why we need them to drink water is that we're raising them for our food, right? I like to eat bacon. Bacon comes from pigs. But the pigs need to live, so they need drinking water. Now, there are different standards, by the way, for human drinking water versus livestock drinking water. Well, I think we're probably not quite as, we're concerned. Maybe not quite as concerned with the water that our animals drink. Okay. What does irrigation mean? Seabass, take it. Exactly, yeah. Irrigation is when we're watering plants and stuff like that, right? Farmers worry about irrigating their crops. But I mean, really, like, I irrigate my flower garden in a way, right? I need to use water for my flower garden. Now, I don't know about you guys, but we have, in my backyard, I have rain barrels. Anybody have a rain barrel in their backyard where you, like, try to save the rain from the roof of your house? I would not drink that water. It's kind of gross. Okay? It's got, like, bugs and little bits of leaves inside of it. However, I have no problem using that water to water my plants. Does that make sense? So, different qualities there. And then the last one here, we also want to consider water because we want to protect aquatic life. Okay. For example, sometimes we save the aquatic life and we put them in things like marinas, or like we have aquariums of fish. But like we want to be careful that we don't kill the fish and animals in rivers and lakes and streams. So those are our 5 main categories of water. We drink it, we use it for play, our food drinks it, we use it to water stuff, or we try to save our aquatic life, like say at SeaWorld, for example. Here's what I need you guys to know. There are guidelines for protecting the humans, animals, crops, and other organisms. Okay? And depending on what you're using the water for, depends on the guidelines. I would imagine the strictest guidelines are probably for human drinking water. Whereas irrigation, like I mentioned, right? When I'm watering my plants, I don't mind if the water is a little bit murky or gross, because it's just the plant that's using it, right? I'm certainly not drinking it, though. So what we're going to talk about today is some of the ways that we figure out how good, how safe, how appropriate the water is for being used. And my next slides have either biological indicators or chemical indicators. And these will let us know how good the water is. So let me give you the first one. A biological indicator could be something like a microbiological indicators. Okay? This could be something like bacteria. For example, let's say you go camping or hiking, and you want to drink some water out of the river nearby. That might be a bad choice, because that river could have bacteria in it. Something like, say, E. coli. It could make you quite sick. If you've ever heard of something called beaver fever, it's basically where you drink river water and then you need to go to the bathroom for a long time. You get where I'm going here. So If there's bacteria in the water, that can be a problem. And often we need to treat this water before you drink it. Okay. Here's other indicators of things. Invertebrates are also a good indicator as to the quality of the water. Now, if you don't know the word invertebrate, it basically means anything without a backbone. Guys, focusing here. Okay. So here's some things without backbones. Insects, shrimps, worms, clams. And depending on whether or not those species are in the water will tell you how safe the water is. Okay. In a way, these two things are opposites of each other. If you have bacteria in the water, that's probably not a good thing. I don't want to drink water that has E. coli in it. That's bad. Okay. So if there's bacteria in it, that's probably a bad thing. However, let's say that I see some water and I see shrimp living in the water or clams living in the water. That's probably a good sign. Does that make sense? Because if something else is living there, it probably means the water is safer. You get what I'm saying here? So if I were to look back at these pictures right here, I can't guarantee for you that this water right here is perfectly safe drinking water, but I see a really good sign. I see fish. That's a good sign. Does that make sense? Because if I see fish, it must mean that it's probably not too acidic because the fish are surviving. So if you see a lot of invertebrates in the water, it can probably tell you whether or not it's safe. And we're going to talk about a couple of abiotic factors on the next slide here. You guys remember the word abiotic from the first unit? Things that are non-living. Okay? We're going to talk about things like temperature, dissolved oxygen content, and pH. Okay? Here's actually a bigger list of them. Here are some of the factors that affect organisms living in the water. Here's the big list. Again, if I could give you guys a little bit of a suggestion, maybe make sure you're aware of all of these. You probably know some of these words before. First one is dissolved oxygen. There is oxygen in the water, actually. There's like bubbles of oxygen inside. And depending on how much oxygen there is, that depends on how much life can survive. Acidity is basically whether it's an acid or not. If it's too acidic, it's going to kill things. But here's some other things you want to monitor, for example. Pesticides. How could pesticides end up in our water? What do we use pesticides for? Yeah, farmers use it. Okay, guys, I'm going to need to call a few of you guys out here. This is not our best day for paying attention, okay? Please. Okay, even if you don't even have notes in front of you, which isn't a good sign, I need your best attention, okay? Pesticides. Yeah, farmers use these to keep things off of our crops, right? But they end up in the water supply eventually, right? I don't necessarily want to be drinking pesticide water. Heavy metals are another one. I've got a slide talking about heavy metals in the future here, but those are bad things to have in waters as well. We've already talked about salts before. What is one way that salts end up in our water supply, especially in the spring? What do we use salt for in the wintertime? Salting our roads, yeah. And so sodium chloride or magnesium sulfate, those can end up in our water supply after icing our roads, de-icing our roads. And I skipped nutrients. We can also try to test our water for nutrient levels. Some of these things are good. We want dissolved oxygen. That is a good thing. Oxygen promotes life. We do not want heavy metals. Those are bad. Those are toxic. We don't want pesticides. Nutrients are kind of interesting. There's kind of like a happy medium for them. We kind of want nutrients, but we don't want too many of them. I'm going to show you why in a bit. Here's a number I need you guys to know. If the pH drops below 5, in general, fish don't survive. That means if it becomes too acidic, things can't live there, which is why, you know that first slide I showed you there? As soon as I saw fish, it probably means the water is more safe. I don't know for sure. There could still be heavy metals inside. There could still be pesticides in that water. But if I see fish, it probably means it's not acidic, at least. That's good news. Okay. There's also another thing we need to know. We need dissolved oxygen, okay, because that infects insects. Yes? Good. pH stands for powers of hydrogen, and basically there's like a number line here. Right in the middle of the number line at 7 for pH, that is things that are neutral. Do you guys recall doing a slide on this in the past? 7 is neutral. What is a neutral substance? What is the neutral substance? Yeah, water. Yeah. 7 is good. Over here on this side, it's an acid. So numbers like 1, 2, 3, 4, 5, and 6, those are acidic. If you have a pH of 1, that is very acidic, like stomach acid. Whereas on the other side, you have bases. And bases have a pH of like 8, 9, 10, 11, 12, 13, 14, like that. Okay. Drain cleaner is very basic. Okay. Really, in general, unless it's basically right around the 7 range, we really shouldn't drink that. We don't drink drain cleaner. We don't drink acid. Yeah. Yeah, now there are some things that are closer there, like for example, citric fruits can be a little bit there. You can actually taste the acidic content though, if that makes sense. So, I mean, yeah, there's a bit of a range. You can probably go down to about here safely. Good call. Lemon juice, for example, is quite acidic. I believe milk, I think, was around 8 or 9. Does that make sense though? That's the scale for pH. So long story short is as soon as you're starting to hit a pH of 5 or lower, it's too acidic for life to live, and fish will start dying. The other thing I wanted to start talking about here is dissolved oxygen. You guys ever like pour water into a cup from the tap and you see like bubbles in the water? That's dissolved oxygen. Okay. We want oxygen in our water supply because things need oxygen to live. Okay? And so we also need that. And I've got some slides on that. So let's talk about dissolved oxygen. I actually have that one up next. Okay. We need dissolved oxygen to be generally above 5 parts per million. This number right here. A little bit later, I'm going to show you how a parts per million works. But maybe note this. We need to have some oxygen in our water in order for organisms to live. Now, here are some things that affect how much oxygen is in the water. Number 1, temperature. If it's too hot or too cold, that can affect how much oxygen is in the water supply. You guys know the word temperature. But maybe you don't know this word. Turbulence. What does turbulence mean? Okay, we know this word from airplanes. When airplanes go up and down and they kind of shake a little bit, that's turbulence. I want to show you this picture again here. This lake right here probably does not have a lot of dissolved oxygen. And the reason why is that it's very smooth, it's very clear, there's not a whole lot of like motion happening. I don't have a picture of it, but imagine a river. And this river has rapids in it. So much so that like you can actually like see where like the water goes kind of like, you know how it goes kind of like white a little bit there? That is going to increase the amount of dissolved oxygen because there's a lot of turbulence there. When water is moving, like on, say, rapids, that's going to increase the amount of oxygen content. The ocean will have lots of dissolved oxygen content. A water bottle that is just sitting there, completely flat, doing nothing, less oxygen in it. Does that make sense? But if you have like a rushing stream or a rushing river, that's a good thing. But here's another one, photosynthesis. We've talked about photosynthesis before, but let's do a quick recap. Photosynthesis is how plants nearby, they use carbon dioxide and they use water to make sugars and oxygen gas. And it also requires light. Do you guys recall doing this in chemistry a little bit? It was one of the 4 equations you had to know. Carbon dioxide and water plus light means a plant is going to produce oxygen gas. Well, if there are a lot of things that undergo photosynthesis nearby, there's now going to be more oxygen. So any plant life nearby can help the oxygen. However, the number of organisms using the oxygen will actually decrease it. Plants will increase your oxygen amount. But if there's like a million bugs and animals and species nearby, that'll actually decrease your oxygen. And that's what this blurb here talks about. I'm going to do something I rarely do. I'm going to literally read my notes directly off the slide here, and then I'll try to add to it. Phosphorus and nitrogen are actually very important too. But too high a concentration is a problem as well. Here's why. Sewage and fertilizers can increase the amounts of these elements, phosphorus and nitrogen. And when you have too many of these elements, it causes an increase in algae and plants. Okay. What does fertilizer do? Causes plants to grow. And if fertilizers end up in our water supply, it causes too much algae. Do you guys know what algae is? It's like a scum kind of like layer that you might see like on rocks or something like that, maybe at the bottom of a lake there. It's like where plants, like really dying plants grow. Okay? Now when the algae die, you know what ends up happening though? It increases the food for bacteria, because bacteria eat algae. You know what bacteria do though? Bacteria use your oxygen. So it's a very long, complicated process here. Here's the too long didn't read version. If you have too much nitrogen or phosphorus, it can reduce your oxygen through this reasoning. Phosphorus and nitrogen are fertilizers, and they make more plants grow. But these plants will then die. And when these plants die as algae, bacteria will feed on them. And what do bacteria do? Bacteria use your oxygen. So in a really long, convoluted sort of process, that's why we don't want fertilizers in our water supply. Because you might say, fertilizer just makes stuff grow. It's good for it. It's too good for it. Does that make sense? There's like a happy medium. It's like the Goldilocks story. There's too warm and there's too cold. We want it right in the middle. If you have too much fertilizer of these things, phosphorus and nitrogen, it causes plants to die. And I've got a picture here illustrating it here. Here's a whole bunch of fish living. This is a nice healthy ecosystem. There is some phosphorus, there is some nitrogen. You can notice that there are some plants growing at the bottom of this lake, but like a healthy amount. Then we bring in a pipe, and there's now sewage, and it's got effluent of nitrogens and phosphoruses. And you might notice what's happened in this picture right here. There's more plants growing underwater. You might argue, plants are good, we like plants. But hang on a sec. These plants die. And who feeds on these plants? Bacteria. And what does bacteria do? Uses up all the oxygen. What do fish need? Oxygen. That's how the fish die. Does that make sense? Cool, moving on. Okay, my next slide's about acidity. Oh my goodness, it's Monday, isn't it? Some of you guys are not giving your best focus. Acidity. If you have things that are too acidic, it can also kill things. Normal pH ranges for snow and rain is about normal pH for rain and snow is about 5.6. And there's a reason for that. Our normal water is actually slightly acidic, and it's due to carbon dioxide. CO2, carbon dioxide, has the ability to form this acid right here. It's called carbonic acid. And you might be able to notice that its chemical formula makes a lot of sense. I want to try to explain why. You guys know CO2 is carbon dioxide, right? Carbon dioxide, when it gets added to water, when you literally combine these compounds together, do some math here. See how there's two H's right here? This now has two H's. There was one carbon right here. There's one carbon right there. There's two oxygens, and then there's one more hidden over here in the water. That makes three. There's three over here. This compound right here is called carbonic acid, and it naturally forms in water anytime water and carbon dioxide mix together. So it's actually normal for rain and snow to be slightly acidic. Slightly acidic, though. 5.6, we're still good. But if you drop the pH lower than 5, like down to, say, 4.5, the lower is more acidic, right, by the way, right? Low is acidic. Then that kills your plants and animals. And so this becomes a problem. And so if you have too much acid in your water supply, it kills things. Here's a picture that I found online. This is known as spring shock. Basically, every spring, you know how like the snow and ice is going to melt? Well, when snow and ice melts, it releases built-up carbon dioxide in the snow, and basically the carbon dioxide dissolves in the water, and it becomes too acidic. And so when it melts, the water temporarily becomes too acidic, and all these fish die. And so you can actually see this phenomenon once in a while, where there's a whole bunch of dead fish along the sides of the river. It means that this river is too acidic. Slowly, though, over time, hopefully it'll kind of balance itself back out. Okay, let's talk about pesticides for a bit. Pesticides are another thing that we like to use to try to promote agriculture, right? Farmers, they want to use fertilizers. They want to use insecticides and keep bugs from eating their crops. However, there's a few problems. Here's the first problem. Resistance. If you ever haven't heard this word before, resistance means that eventually the insects, they learn, they evolve. Remember talking about natural selection? Through natural selection, eventually some species will will actually become resistant to the pesticides, and the pesticides don't work anymore. So then you have to use stronger pesticides. But then species become resistant to that, so you have to use stronger pesticides. And eventually, you're using such strong stuff that here it becomes the problem. It becomes ingested by organisms other than the targeted ones. And so we're trying to kill this bug, but something else eats it and dies instead. And then it causes a problem. Or here's another problem. Our pesticides become so strong that they mix and form a much more toxic substance than you originally want. So in general, pesticides are good. I think there was a stat I showed you previously where like over half the world's food supply would be lost if we didn't use pesticides. But we got to be careful. We don't want to use them too much. Okay, heavy metals. You guys may not be familiar with heavy metals, so I need to talk about these a little bit. Heavy metals are anything which is 5 times more dense than water. If something is 5 times thicker than water, it's considered a heavy metal. And we've discovered that many of these things lead to cancer or like brain damage, even death. So we want to be careful around the heavy metals. Literally, we call them heavy metals because they are dense. The most dense material that we know of is lead. What do we use lead for in the, what was that? Well, that's actually carbon. What do we use lead for in medical offices as a protection? Anyone go to the dentist recently? What is that? I think you have the idea. If you have an x-ray, yeah. Anyone ever had x-rays at the dentist before? They put the big coated thing on top of you? You know what I mean, like the little smock thing they put on top of you when you get x-rays done, right? Or at the dentist. That is made of lead. And the reason why it's made of lead is that it's very dense. So dense that even x-rays can't go through it. Anyways, okay. Here's some other metals that are very dense. Copper, zinc, mercury, cadmium, arsenic, and nickel. And these are naturally occurring things in rocks and soil. But here becomes the problem, though. Batteries. Batteries are made of cadmium and nickel. And when you throw batteries into the garbage and they end up in the landfill, these chemicals, they leach into our soil, they leach into our water supply, and now there's cadmium in our water. And that's not good because it can lead to brain damage or cancer or death. Okay? Same thing with tires and gasoline and paint, which is why, guys, we want to recycle these as much as we can. We don't want to throw them in the garbage. Yeah. There should be a collection site, and you should be able to bring them to the dump and have them be collected so they can hopefully get either incinerated properly or maybe even reused. Yeah. But in theory, yeah, we don't want to throw them in the garbage because that, yeah, it leaches into our soil and into our water supply. Okay, now, here's a term I need you guys to know. I already used it earlier in our lesson. It's called a ppm. It stands for a part per million. And a part per million is a very, very, very small unit of measurement. Basically, it means that you have 1 in 999,999. Now, maybe that seems kind of weird to do, but what would happen if you took this number right here and added 1 more to it? What would this number plus 1 be? 1 million. So what we're really saying is that you have 1 out of 1 million. Okay? Because really, it's this one plus 1 more, plus the one you actually have. That's a part per million. Now, most toxic things like heavy metals or pesticides, you don't have a lot of them. When we measure them in parts per million. As like an example, if you had 1 part per million, just so you guys can imagine this, imagine a swimming pool, like a full-size swimming pool. A part per million would be you adding 1 1/4 2-liter bottles of pop. Okay, you know how like you go buy a 2-liter bottle of pop there? If you were to add this much into a big swimming pool, that would be a part per million. It's not very much because according to dilution, it's going to spread out a lot. Okay? But still, if it's a toxic substance or a heavy metal, that can be an issue. Sometimes you might even see this, ppb. What do you think ppb stands for? Parts per billion. That's even more dilute. Okay? This is almost guaranteed to be on your PAT. Almost 100% guaranteed. They're going to ask you a question about how to calculate something in parts per million. So let me do an example. Let's say that we have 1,000 milliliters of water. and we drop in 0.03 milliliters of food coloring, how many parts per billion do you have? Let me show you how to answer a question like this. It's actually not that hard. I just need to show you how. What we're going to do is we're going to take 0.03 milliliters and we're going to put it inside of 1,000 milliliters. Okay. This, it's almost like you have a big container of water and we're going to put 1 drop inside. It's not a lot, but is it enough to be a problem? Now, if you want to calculate something in parts per million, it always works like this. What we're really trying to do now is calculate an unknown amount in a million. So here's how you always set these up. The 2 numbers I'm going to give you go over here as like a fraction. This is what's getting put inside of this. 3.3 milliliters goes in 1,000. And what we want to do is we want to figure out how to make this into a million. Okay. Now there's a couple of ways you can solve this. Okay. One of the ways you can solve this is cross-multiplying, if you understand how to do that in math. Okay. So if you understand how to cross-multiply, all you have to do then is times by a million on both sides. If I times by a million here and times by a million here, we'll have our answer. So I've got a calculator on my computer. I'll show you how this works here. Okay. So the original fraction would have been 0.03, and we divided that into 1,000. Oh, there we go. Divided that into 1,000. All we have to do then is to make it into parts per million is times it by a million. 1, 2, 3, 4, 5, 6, 7. I think I have a million now. Let's see, that's 6. There we go. If I do this, this will tell me that I have 30 parts per million. So if I go back to my notes here, all I had to do to solve for x was take these 2 numbers and divide them by each other, and times by a million, I now have 30 parts per million. So in every million drops of water, 30 of them are food coloring. Okay. So that's one way you can solve this. Guys, you're not giving me your best attention here. Here's another way of solving it. If you don't like that, that's fine. Here's another way of doing it. What you have to do otherwise is kind of figure out, well, how do I take... Okay, Seabass, go for a walk. This isn't working, buddy. Oh, sorry, are you just joking? Sorry, I thought you were laughing at it. Sorry, go ahead. Okay, stay with me though, okay? Because you haven't been most of this class, eh? Sorry, I'm behind you. I didn't know that you were coughing. Another thing that you can do here is you can try to figure out how do you turn the number 1,000 into a million. How do you turn the number 1,000 into a million? You have to times by 1,000. If you take 1,000 and times by 1,000, you get a million. Well, then all you have to do on the top is take 0.03 and times it by 1,000. Well, what is 0.03 times by 1,000? 30, which means you have 30 parts per million. Let me try another example here, okay? I only have one in my notes, but I want you guys to know how to do this because I feel very confident this is going to be on your PAT. So let's do an example. Let's say that we have 2,000 milliliters of water, and we add 5 milliliters of, I don't know, what are we adding? Toxic substance. Let's figure out the parts per million. So here's how you do this. We're adding 5 milliliters into 2,000. And we want to figure out how many it's going to be as though it was a million. So option 1, cross multiply. If you like cross multiplying, just times both sides by a million, times this side by a million, and all you need to do is do 5 divided by 2,000 times a million. You're good to go. Let's try it. 5 went into 2,000. It's not a lot, right? 5 out of 2,000, that's not a lot. But then times by a million. 1, 2, 3, 4, 5, 6. Okay. This is a lot more toxic. This is 2,500 parts per million now. That's a lot. So X was 2,500 parts per million. So that's one way of doing it. Okay, if you don't like that method, if that doesn't really make sense to you, here's another option. You got to figure out, how do you get from 2,000 to a million? What do you need to times by to get from 2,000 to a million? And if you're not really sure what to do, though, just divide the two numbers. Is it 500? I think it's 500, yeah. So if you times 2,000 by 500, you get a million. Well, then all you got to do is take 5 and also times it by 500. So what's 5 times 500? 2,500 parts per million. So it's actually quite easy to do. What I foresee happening here is maybe they'll ask you a question. They'll give you this information right here. And then they'll tell you something like this. Anything over 100 parts per million means you'll die. Then the question will be, is this toxic? Well, for this question here, 2,500 parts per million, yeah, it's toxic. But what about this one back here? Would this be toxic? No. Okay. So, anyways, I want you guys to know how to do parts per million. Okay, I'm almost certain it's going to be on your PAT. So, oh wait, last slide, then we're done. This is my last slide, right? Yeah. There's another way that we measure things as well. Okay, when we're measuring things like heavy metals and toxic substances, things that are poisonous, one of them is parts per million. The other one is known as an LD50. LD50. Okay, here's what it stands for. Lethal dose. Basically what it refers to is this is how much you have to give something before half of the population will die. 50 stands for 50%, half. Okay, so basically here's the idea. I'm going to use this table down here. You can actually die by eating too much salt. Okay. For example, the LD50 value for salt is 3,000 milligrams per kilogram. Here's what that means. For every kilogram that you weigh, if you eat 3,000 milligrams, it could be fatal. And basically the 50 means that about half people in the world would live, but half would die. Does that make sense? So if you weighed, say, 100 kilograms, if you took 3,000 milligrams for every 100 kilogram that you weighed, there's a 50-50 shot that you would die because you've eaten too much of it. Okay? Do you want to see a high LD number or a low LD number than if it's really poisonous? The more poisonous it is, the lower the number is. So if you have like DDT, a pesticide, it has an LD50 number of 87 milligrams per kilogram, which basically means this small number here means it's more toxic because you don't need to ingest nearly as much to die. Okay? You can actually die from eating too much salt. But like, let's do some basic math here. Let's say that you weighed 100 kilograms even, just for the sake of a round number. If you weighed 100 kilograms, you would need to eat 3,000 milligrams times by 1,000, which would be like 3 million, oh, that's one too many, 3 million milligrams of salt. I can't even fathom how many milligrams of salt you'd be eating to eat 3 million milligrams of salt. But if you did, you could actually overdose on salt. You can also overdose on, say, something like caffeine. So, long story short, the lower the number, the more toxic it is. And why do we call it LD50? Because the 50 means that, like, chances are 50% of all test subjects who eat this, they died. We usually test them on rats, by the way, because we're not actually going to test this on humans. So, okay, that's my notes. Let's summarize what we learned about today. We'll work backwards. At the end of our notes, we talked about 2 different ways of measuring how toxic something is. One of them is LD50, and one of them is this parts per million thing. I need you to know how both of them work. Okay. We also talked about different things that affect our water quality. There's a big list here. Oxygen, acidity, pesticides, nutrients, heavy metals, and salts. All of these things are either good or bad for our water supply. Most of them are bad, but we do want oxygen. Oxygen is needed. We do want nutrients, but some nutrients. Tyson, focus. I know it's Monday, guys, but give me your best attention for 2 more minutes. Okay. Other things we discussed is that there are different sources that we use our water for, from our drinking to irrigation to just saving animals or recreational uses. Okay. And then the last thing we should talk about, do you know the difference between a biological and a chemical indicator? We talked about two biological indicators. If there's bacteria in the water, that's biological because they're alive. That's not good. We don't want bacteria in our water. Or maybe you're looking at aquatic invertebrates like insects and shrimp and worms. That's actually good. I may not necessarily like to have worms nearby, but it's a good indicator that the water is safe because if the worm can live, I probably can too. The chemical indicators then are these ones here. These are your chemical indicators, whether or not you have things like oxygen, whether or not it's acidic or not, whether or not there's pesticides or heavy metals, because usually in general, all of these things are bad for our water supply. Okay, any questions? Okay, tomorrow we're going to talk about air quality, and then after that, guys, we are almost done this unit in terms of like me talking at you, okay? So last thought here, you guys have about 20 minutes left.